The Gross-Neveu-Yukawa (GNY) model, a fermionic quantum critical point in 2 + 1 d, is expected to exhibit converged critical exponents across various methods, including conformal bootstrap, perturbative renormalization group, and quantum Monte Carlo (QMC) simulations. However, lattice QMC simulations have been hindered by the ultraviolet (UV) finite size effect. To address this, the authors employ the elective-momentum ultrasize (Emus) QMC method to compute the critical exponents of the O, N, 2Z2 Ni chiral Ising transition on a 2D pi flux fermion lattice model. The GNY model, involving Dirac fermions coupled with a scalar bosonic field, is a simple 2 + 1 d universality class with significant theoretical and experimental implications, including applications to Dwave superconductors, nematic quantum criticality, graphene, and other quantum materials. Despite its importance, consistency in critical exponents has not been fully achieved, particularly for the chiral Ising transition with O, N, 2Z2 global symmetry. Previous studies using E-expansion, conformal bootstrap, and lattice QMC simulations have yielded closer exponents over the years, but significant deviations remain, especially in the bosonic anomalous dimension exponent f. The Emus QMC method matches fermionic and bosonic momentum transfer and collective update in momentum space, providing fully consistent exponents with those obtained from bootstrap and perturbative approaches. The results are presented in Table I, which compares the Emus QMC exponents with previous QMC results and those from the latest E-expansion and bootstrap estimates. Notably, the Emus QMC method demonstrates the potential to overcome the challenges associated with the UV finite size effect and achieve consistent critical exponents for the GNY chiral Ising transition. The author's work contributes to the development of many-body methodologies and enhances our understanding of quantum phase transitions in interacting Dirac fermion systems. The limitations of previous studies, including the finite size effect and the difference in velocities of critical modes, are acknowledged. The authors highlight the need for better model design and algorithmic developments to overcome these challenges and achieve consistent results with bootstrap and E-expansion for GNY chiral Ising universality classes. The chiral Ising Gross-Neveu-Yukawa (GNY) model is studied using the elective-momentum ultrasize (Emus) quantum Monte Carlo (QMC) method. This 2D pi flux fermion lattice model exhibits a transition between the Dirac semimetal (DSM) and quantum spin-Hall insulator (QSH) phases. The Emus QMC method computes the critical exponents of the n = 8 chiral Ising GNY transition, described by the Lagrangian, which includes fermion, boson, and coupling terms. The lattice model consists of 2 boson and 2 fermion sites per unit cell, with fermionic hopping terms generating a pi flux in each plaquette. The bosonic field is coupled to the fermions with strength lambda equals plus or minus 1, depending on the boson sublattice. The Emus QMC method simulates 2 patches near the Dirac points in momentum space, allowing for high accuracy computation of critical exponents with reduced computational cost. The results show the crossing of the Rg invariant ratio with small drifts, and the stochastic finite size analysis finds fully controlled exponents, in agreement with previous bootstrap and E-expansion results. In the chiral GNY model, N 4-component Dirac fermions interact with a bosonic scalar field phi. The coefficient m in the m⁵2 term of the bosonic Lagrangian has a critical value m_c, below which the bosonic scalar field spontaneously acquires a finite expectation value, giving a mass to the fermions, the QSH phase. Above m_c, the expectation value of phi vanishes, and the fermions return to the massless form, the DSM phase. At m_c, the system is expected to flow to the chiral GNY CFT. Notably, there are 2 different GNY models with the same number of fermions but different global symmetry groups. This work focuses on the chiral GNY model with O, N, 2Z2 global symmetry, where the differences between the scaling dimensions of external operators are very small, tilde operator 3 × 10⁻⁶ for n equals 1, 2, 4, 8. The EMUSQMC method has accessed larger system sizes and better data quality with reduced computational cost, enabling high-accuracy computation of critical exponents. The results have implications for the study of interacting Dirac fermion systems and the exploration of the chiral GNY archipelago. The chiral GNY Ising CFT is a quantum field theory that describes the critical behavior of a chiral GNY model. The Hamiltonian of this model consists of three components: L_fermion, L_boson, and L_coupling. L_fermion describes fermions with nearest neighbor hopping and a phase factor that introduces a pi flux in each plaquette, resulting in two Dirac cones at specific points in the Brillouin zone. L_boson describes the scalar bosonic field with an imaginary time derivative term, mass term, and interaction terms up to fourth nearest neighbor. L_coupling is a next nearest neighbor hopping for fermions, determined by the boson sitting on the bond and the difference of two boson sublattices. The EMUSQMC method is employed to simulate the model, focusing on the linear dispersion of Dirac cones in the Brillouin zone. To simplify the model, it can be rewritten with a single Dirac cone covering most of the Brillouin zone, such as the slack fermion. However, this approach requires consideration of the Nielsen-Ninomiya theorem. Simulation results are presented in Figure 2, showing the square of the bosonic order parameter S, gamma, and the correlation ratio R as a function of the control parameter M for different system sizes L equals 12, 24, 36. The data collapse of S, gamma, versus M and the stochastic analysis of the error bound of 1, nu, eta_phi, are also shown. The analysis yields the values of 1, nu equals 1.07, 12, and the bosonic anomalous dimension eta_phi equals 0.72, 6. The color bar in the stochastic analysis represents the fratio of the goodness of fit, with the red dot indicating the set of exponents used in the collapse. The results demonstrate the critical behavior of the chiral GNY model, with the bosonic order parameter and correlation ratio exhibiting a clear dependence on the control parameter M. The data collapse and stochastic analysis provide strong evidence for the universality of the model, with the extracted exponents consistent with the expected values. The Gross-Neveu-Yukawa (GNY) model's critical exponents have been accurately captured using the EMUSQMC method, an alternative to conventional lattice simulations. By focusing on the momentum space near Dirac points, the EMUSQMC method simulates the linear region of the model, effectively rendering the simulation of a different model with the same dispersion near the Dirac points as the original one. System sizes up to 36 × 36 have been simulated, with reduced computation time and human effort. The EMUSQMC results show a significant reduction in finite size effects, with a much smaller drift in the crossings of RG invariant ratios compared to previous studies. To extract the GNY critical exponents, the magnetic structure factor of the bosonic field has been computed using the equation S, Q, equals 1 per liter squared phi q phi minus q equals 1 per liter to the power of 4 underscore I j e caret iq ri rj phi I phi j. The correlation ratio R equals 1s, gamma plus delta q, s, gamma, has been used in conjunction with the s, gamma, to obtain the critical exponents. The results show that the EMUSQMC simulation yields values of 1, nu equals 1.07, 12, and f equals 0.72, 6, which are consistent with previous studies. The imaginary time Green's function has been monitored to obtain the fermion anomalous dimension EPS. By utilizing the Lorentz symmetry at the GNY Ising CFT, the imaginary time decay of the fermionic and bosonic Green's function has been analyzed, yielding a value of EPS equals 0.04, 2, using the equations GF tau equals 1 per liter squared underscore k psi k tau psi k 0 proportional 1 tau caret 1 plus EPS and G flat tau equals 1 per liter squared underscore q phi q tau phi minus q 0 proportional 1 tau caret 1 plus f. The stochastic data collapse analysis has been performed to unbiasedly determine the optimized critical exponents, and the results show that the EMUS-QMC simulation yields consistent values with previous studies. The analysis has been repeated 1,000 times with random noise added to S, gamma, to estimate the error bound for the optimal exponents. Overall, the EMUS-QMC method has been demonstrated to be an effective approach to simulating the GNY model, yielding accurate results with reduced finite size effects and computation time. The Gross-Neveu-Yukawa (GNY) transition in two-dimensional systems is comprehensively studied using the Emus algorithm, a novel quantum Monte Carlo (QMC) method. This work aims to achieve textbook-level consistency of critical exponents for the n equals 8 chiral Ising GNY model with conformal bootstrap and epsilon expansion results. The GNY model is fundamental for understanding phase transitions in two-dimensional systems, such as the transition from Dirac semimetal to band insulator in graphene and twisted bilayer graphene. It is also crucial for understanding various phenomena in condensed matter physics, including superconductivity, nematic order, and intervalley coherent and valley polarized orders. The Emus algorithm, an extension of the auxiliary field QMC method, is introduced to simulate the GNY model. It utilizes the Hubbard-Stratonovich transformation to introduce auxiliary fields, which can be integrated out to obtain the original action of the GNY model. The Emus algorithm offers advantages, including the ability to simulate systems with large numbers of fermion flavors and its potential for studying other GNY transitions. Simulation results for the n equals 8 chiral Ising GNY model report critical exponents 1, nu, eps, f, consistent with conformal bootstrap and epsilon expansion results, demonstrating the robustness of the Emus algorithm. The discussion section provides an overview of the results, comparing them with previous studies using QMC, epsilon expansion, and conformal bootstrap. Notably, the present Emus QMC simulation requires less computational resources compared to previous work and can be easily extended to other chiral GNY islands with different numbers of fermion flavors and symmetries of the bosonic field. The Emus algorithm has potential applications in exploring various phenomena in two-dimensional systems, including superconductivity, nematic order, intervalley coherent and valley polarized orders, as well as superconductivity in graphene and twisted bilayer graphene and kagome metal systems. It is anticipated to play a crucial role in understanding conformal field theories and realistic two-dimensional quantum materials. The elective-momentum ultra-size, Emus, quantum Monte Carlo, QMC, method is a powerful tool for studying the universal properties of lattice models. Building on previous studies that applied the momentum space QMC method to various lattice models, such as the Heisenberg model and the Hubbard model, recent works have further developed the EMUS-QMC method, significantly improving its efficiency. A crucial component of the EMUS-QMC method is the stochastic data collapse technique, which enables unbiased extraction of critical exponents by analyzing the scaling behavior of the data and collapsing curves onto a single master curve. The EMUS-QMC method has been successfully applied to study the properties of various lattice models, capturing their universal properties. Notably, recent studies have employed the EMUS-QMC method to investigate systems with non-trivial topological features, highlighting its power in capturing intricate properties. Further applications of the EMUS-QMC method have focused on systems with strong interactions, such as the Hubbard model, demonstrating its effectiveness in capturing universal properties. The stochastic data collapse technique is a key aspect of the EMUS-QMC method, allowing for the extraction of critical exponents from the scaling behavior of the data. By collapsing curves onto a single master curve, this technique facilitates the unbiased extraction of critical exponents, providing valuable insights into the universal properties of the system. Overall, the EMUS-QMC method has proven to be a versatile and powerful tool for studying the properties of lattice models, with a wide range of applications in condensed matter physics. The supplementary material for Emus live on the chiral Gross-Neveu-Yukawa archipelago delves into the implementation of the EMUS-QMC scheme, a variation of the fermion determinant quantum Monte Carlo DQMC, simulation. This approach focuses on small patches of the Brillouin zone, BZ, that are crucial in the infrared, IR, limit, disregarding the effect of momenta far from these hotspots. These hotspots correspond to the two Dirac points in the present model. The Emus scheme operates in momentum space, offering three primary advantages over traditional DQMC simulations. Firstly, it allows for the elimination of momentum points outside of the patches near the Dirac points, reducing computational complexity. Secondly, this momentum space cutoff for fermions also leads to a cutoff for bosons, as the bosonic system is ferromagnetic with an order vector of gamma equals 0, 0. This results in the suppression of the hopping between the two patches in fermion K space, which corresponds to low-energy fermion excitations by the bosonic Hamiltonian. Consequently, only momenta components within the same patch need to be considered, encompassing a square region around gamma with a length of 2LF and containing 2LF plus 1 squared sites. The model is block diagonalized into 2x2 matrices describing the hopping between two sublattices at each of the n equals LXLK points. The fermion part of the model is given by equation S2, where x_k sigma represents the block diagonal matrix. The coupling term, represented by equation S3, is a summation over two momenta, with the bosonic field terms related to the momentum difference between the two k points. The Emus scheme operates with a system size of L equals 6LF, and the number of sites considered in each patch is NF equals LF plus 1 squared approximately equals N, 36. There is no periodic boundary condition in these small patches, and the left and right sides are not identified. In the smallest possible system size LF equals 2, one is effectively simulating a 12 by 12 system by considering only 9 momenta in one patch, as depicted in Figure 1d. This approach has been successfully demonstrated in previous works on 2D Fermi surfaces coupled to quantum-critical Ising bosons on square and triangular lattices. 4, 32, 33. By working in momentum space, the EMUSQMC scheme provides a more efficient and focused simulation method compared to traditional DQMC, allowing for the exploration of the chiral Gross-Neveu-Yukawa archipelago. The EMUSQMC simulation can be performed entirely in momentum space, allowing for direct updates of bosonic fields on their momentum components. In DQMC, the fermion determinant update involves the introduction of the matrix delta, which represents the change in the coupling term due to the update of the bosonic fields. Using the Trotter decomposition, delta can be approximated as the exponential of the difference in the coupling terms before and after the update, minus the identity matrix. This matrix is block diagonalized by groups of momenta related to the updated momentum Q. For a patch size LF equals 2, updating the boson with momentum Q equals 2 pi L 1 2 to phi Q plus df requires simultaneously updating phi Q with a complex conjugate change phi Q plus df. This relates two pairs of fermions, resulting in a matrix delta consisting of two 2 by 2 diagonal blocks. The fermion part acceptance probability is calculated as the square of the determinant of the matrix I plus delta, Ig. The boson part acceptance probability is computed by performing an inverse Fourier transform on the bosonic field to obtain its real space configuration, calculating the energy difference, and then computing the probability as Rb equals E caret dt delta E underscore B. The full acceptance probability is the product of the fermion and boson acceptance probabilities. To enhance efficiency, the amplitude of change in the bosonic field CQ can be optimized to avoid proposing changes with too small an acceptance rate while still making significant updates. Notably, CQ is larger when the updating momentum Q is closer to gamma, as phi Q has a larger magnitude on average. The bosonic interaction term, phi I phi j, squared can be expressed in terms of Fourier components, reducing the time complexity of the calculation. Due to rotational symmetry, the fermion acceptance probability can be computed in one patch and squared to obtain the overall probability. The remainder of the simulation follows the standard DQMC scheme, with the fermion weight of each bosonic configuration given by the determinant of the matrix I plus B sigma, beta, 0, where B sigma is defined in terms of the coupling term and the fermion and boson Hamiltonians. When an update is proposed, the determinant can be computed using the matrix delta, which represents the change in the coupling term due to the update. The acceptance rate calculation is revisited, with the ratio of weights expressed as a determinant of a matrix involving the Green's function. This simplification yields an expression involving the equal time Green's function, G, which is defined as the expectation value of the product of two fields, psi I, tau, and psi j, tau, evaluated at the same time tau. Combining the two spin orientations and considering particle-hole symmetry, the final expression for the acceptance rate is obtained as the square of the absolute value of the determinant of a matrix involving the Green's function and the matrix increment. This expression is denoted as RF. The discussion then shifts to the stochastic data collapse of the order parameter, as shown in Fig. 2, C, and D. A stochastic approach is employed, similar to that in Ref. 59-60. The data collapse is achieved by fitting a line to the collapsed data, and the goodness of fit is evaluated using the R-squared value. The R-squared value is defined as 1 minus the ratio of the residual sum of squares to the total sum of squares. The residual sum of squares measures the variation between the rescaled data and the fitted value, while the total sum of squares measures the variation of the fitting curve itself. The weights used in the calculation of the R-squared value are chosen to have larger values near the critical point and decay exponentially away from it. This ensures that the process focuses more on the portion of the data near the critical point. The R-squared value is used to evaluate the goodness of fit, with values closer to 1 indicating a better fit. The process of data collapse involves scaling the data obtained from different system sizes according to a set of critical exponents, fitting a single curve to all the points, and calculating the ratio f. If the ratio f is small, it indicates that the set of exponents produces collapsed data that can be explained well by a single curve, and hence the set of exponents is considered better in terms of data collapse. The equations used in the calculation of the acceptance rate and the R-squared value are det I plus b, beta, L increment tau, I plus increment b, L increment tau, 0, det I plus b, beta, L increment tau, b, L increment tau, 0, equals det I plus increment I minus g, L increment tau, L increment tau. R2 equals 1 srays, stat. Srays equals n airy summation, y squared. Stat equals n airy summation, y squared. Where g is the equal time Green's function, increment is a matrix, and y is the y value of the scaled data point.